I'll talk about the hot restart persistence feature which I developed for Hazelcast. Okay, just a short introduction to what Hazelcast is and what is in-memory data grid in general. The easiest way to describe it is as a key value store, which is all in RAM, and is distributed across a cluster. So the majority use case is low latency access to your data. So it's kind of like a distributed cache solution. There can be various things you can put into cache. It's not necessarily a database cache. It could be any expensive operation that you want to preserve the results of. And just a second. There is a problem when you have to restart the cluster, although it's just redundant. You could say cache is redundant data is just cached. It could be rebuilt, but still you lose all the data in the cluster, and you always have a reason. You either have an outage, so you just lose your data without wanting to do it. You also there is always some reason to restart your cluster for some kind of regular maintenance. So what's the problem today? RAM sizes have grown very much. So we are talking about terabytes per node. You can have a cluster which is not so big, 10 nodes, each holds a terabyte of data. That's 10 terabytes. It will take a very long time to rebuild that from scratch, from the original source, or do all the computation again. So more and more customers need this data to be preserved, even though you shut down your cluster, your in-memory storage. So that's how we got to the need to actually build persistence for something that's called in-memory data store. One might wonder, so why don't you just use a database? There's all kinds of embedded databases for Java. Why don't you use that? Why would you rewrite everything from scratch? But we have a very specific narrow use case, which is defined by these items. So we only do writing. We never look up anything from the store. We only reload it on restart. There is no need to arrange data on disk to be easily accessible by key, by some kind of hashing or whatever. It just has to be there to be able to read it. We also have this special requirement which happens when you get a new node, for example. Our cluster is dynamic. You can always add more members to it with no reconfiguration. At that point, data migrates to a new node. And what happens on the existing nodes, you have to delete the data which the nodes no longer own. And on the level of persistence, this has to be reflected. You have to delete the data on the low-level persistence layer, and it would be very expensive if you had to delete each and every key individually, which would be needed if you worked with a classical database. You would just have to say remove this, remove this, remove this, and so on. This would be very expensive, so we had to support a specific bulk delete operation, which is quite specific to this use case. So this is what led us to actually implement our own persistence. We had to decide which general approach to use. Studied a bit of approaches, but usually the approaches are those who promote fast lookup of data. So we ended up implementing something that's not so often found in persistent solutions, but it's inside the community, once you find out which community you have to look for, it's based on this Sprite LFS paper from '92. It gives a general framework, general ideas how to store data in a log structured manner and be able to efficiently manage it and clean it up, especially. So just to give a brief overview what's log structured storage, it means you don't update your data, you just write a log of all update events. Something changes, there's either a put operation or a remove operation. It's very simple. And you just write another entry in your log. Okay, stuff was put in, stuff was removed, and there's this third operation which is specific. For our case, this is the bulk delete operation. We call it clear by prefix because there's a prefix which identifies which exactly data structure it belongs to. So you have a log on disk, system comes down, system comes up. What you have to do, just replay all the events from the log back to the RAM store, and you'll end up with RAM store in the same state as it was before shutdown. So this is all beautiful, this is very fast. You just have to write one record on disk, just append it on the current file. It's a very fast operation. No housekeeping needed there, but the log will grow forever, of course. So you have to do some cleaning. You have to do garbage collection. And this is where all complexity comes in. So we have a system which focuses all of the complexity inside the GC operation. The GC operation, you see this phrase on the bottom, write amplification. This means that your write operation is no longer so cheap as it seems. It is amplified, the price, the cost of this operation is amplified by the need to later on do the garbage collection for this value. These are general goals we had in the design of our system. So we wanted the GC to be concurrent, which means it happens in the background. There is no stop the world event. There is no big latency paid by any one update operation. It should be incremental, which means you cannot just collect all those terabytes of garbage all at once. You have to do it bit by bit in small pieces, which is connected to the first item. If you want low latency, you have to do it incremental garbage collection. We also threw in generational aspect, which means if the user is using your store in a way which is very typical, it very commonly occurs that your write access has this property, which is called the generational garbage hypothesis. And it means if you update a key now, you're more likely to update the same key soon as opposed to any other randomly chosen key. So if that describes more or less your access pattern, then our algorithm will be able to optimize the amount of overhead, right? The overhead will be less if this is satisfied. And the last point is, because we are a RAM store, we have all data in RAM, so garbage collection should not have to read from disk during its operation. It has all the data ready in RAM if it needs to, because typically garbage collection means some copying of data. You have to separate live data from garbage, and that means copying live data. And in our case, you don't want to copy from the disk because it's there in RAM. So these are like the high-level features of our algorithm. This slide explains the part with gerational garbage collection. what do we achieve and how we achieve it. What we do, maybe I should step back and just describe generally how this garbage collection is performed. So first of all, there isn't just one big log file as it's simply presented. There are actually segment files. One segment is 8 megabytes. So we have many files, each is 8 megabytes in size. And we keep metadata. We know exactly for each of these files how much garbage is in this file. So we know, okay, this much is live data, this much is garbage. We know this for all files. So we have this kind of picture. This is what our system knows about our files. And now when the decision to go into garbage collection arrives, first you have to pick some of these files to be garbage collected. So usually, well, you would choose those with the most garbage, right? Then we apply this trick from the Sprite LFS paper. It's quite a simple trick which gives us this optimization for generational garbage. We don't just copy the data directly as it was stored in the same order as it was stored. Rather, we sort all the data from all the files that we are about to copy. We sort it by age or by birth date or whatever you want to call it. But internally it's our sequence number of a record. And then we write this sequentially to disk in this order. This results in some files getting just the old data and other files just getting the new data. So now, because we assume old data is not touched often and new data is touched often, it comes about that you get these kind of segment files where you quickly lose all the live data within them. And on the other side, you get these kind of chunks. We call them chunks, not segments, they're just a word, where you have very little garbage. So now you're in a very good position when you go into garbage collection. You choose these two, you free all this garbage, this is your win, this is your benefit, and you just pay for this amount of data being written to disk. This is the trick we use to get lower overhead. Our goal is to get rid of certain amount of garbage, and the cost we have to pay for it is the amount of live data that's trapped together with this garbage. So our goal is to have chunks like this, where you can get rid of a lot of garbage and pay little cost. This is already a slide for reloading. I would like to mention something more about updating. How we organize the procedure during runtime. You have to have a streamlined manner of writing data to disk. What's the issue? You want to write from a single thread, basically. You want to write to just one file at a time and not have many threads going to the disk at once. There will be competition between them. You would be doing random access to the disk. It just doesn't benefit. No, parallelism at this level doesn't benefit you. So at one side, our RAM store has many threads which deal with RAM-based data, but we want to have optimally just one thread that does the writing. So we gather all this data from all the, we call them partition operation threads. We gather all their operation and we have a dedicated I/O thread which writes to the disk. And then we have another GC thread which keeps count of what's going on in the hot restart store and decides when to go into garbage collection. So in the end you have two threads. One is writing business level data. It's writing the events as they happen, and the other one also wants access to disk, but for the purposes of GC. So you still have competition between two of these threads, but it's better than just having each of the partition threads, which would be as much as you have cores on the CPU. It would be much worse. And this slide is already talking about the reloading phase. During reloading, things are quite different. Actually, it turns out, I'm still not sure how general this is, but we have an SSD system which is no longer cutting edge, but let's say it's still high end. It's directly connected to the PCI Express interface, but it uses this SATA protocol. The newer generation is connected to the PCI Express bus and also uses an NVMe, an Intel protocol, which is specifically designed for SSDs, which are no longer even called SSDs, just non-volatile memory storage, which we didn't test with. So I'm telling you the story with PCI Express connected SATA protocol disks. It turns out that you cannot just read from one thread and exploit the full bandwidth that the disk can offer, SSD. We got 1 gigabyte per second, or even not that, 0.8 gigabytes per second by one thread, and if we employ 4 threads or 8 threads, suddenly we can reach almost 2 gigabytes per second from the same one disk. So we wanted to exploit this in our reloading procedure. We want to be as fast as possible. So we arranged for this pipelined architecture where there are as many I/O threads as you configure. So you can configure 1, you can configure 4 threads. You choose the number that's optimal for your system. So they read in data in parallel, then they scatter the data to all the partition threads. There are any number of threads. It's defined by a completely different parameter of the system. It's the number of cores in the system, and then they gather back to just one GC thread corresponding to one I/O thread. So in this way, we exploit both parallelism in the SSD at the level that's optimal for it, and the parallelism that's optimal for the RAM store, because RAM can tolerate many more concurrent operations. This is as it looks in a picture. So this is the case with one I/O thread. If you configure 4 parallel I/O threads, you'll just have 4 of these pictures in parallel. This is the scheme we use. And now, at this point, I wanted to show you a live demo. 5 minutes left. Unfortunately, I couldn't connect the laptop where I have this demo on. But I can just explain a bit about this picture. This shows an instant in the operation of the hot restart store. It's not reloading, it's regular operation. So each of these, it's divided in vertical lines. Each thin line, just 1 pixel wide, corresponds to one of these chunk files. Blue is live data, gray above is garbage, and here this red data is flagged for garbage collection. So we are now in the middle of garbage collection. You can see the GC chose the chunks with very little live data, and it's copying them over here. And you can see many things here, many artifacts of the way the algorithm works. These would be the chunks from previous GCs, which are full because they contain all data. Beside them would be other chunks with fresh data which quickly turns into garbage. It's much more fun when it's animated. These are some factors to consider which affect performance. It's not trivial to find the best level of parallelism which brings out the best performance. The whole system is quite sensitive to the size of your entry because there is a fixed cost per entry, per key value pair that you have to pay. It doesn't matter how big it is. It's always the same cost. You have to do some hash lookups, hash insertions. You have to, during reloading, you have to parse a header. It's all fixed cost per key value entry. So if you have very small entries, you'll have big overhead from this fixed cost. And then this pushes your choices for tuning in the direction where you want to parallelize stuff, so you can process this fixed overhead in parallel. And overall, you will not be able to achieve the best throughput. In the opposite cases where you have large entries, this is like the easiest case to handle because it's more I/O oriented. You do just a little bit of housekeeping work and then you just read the data or you just write the data in the opposite direction. In this case, when you have large entries, parallelism can be lower to achieve the best throughput. Here are some benchmark results for our store. So I measured in the lab that I mentioned and also on EC2 instances, standard instances on Amazon. These are some specs. So there's 10 cores per socket. There's 2 sockets, so we have 20 cores and it's 40 hyper-threaded cores. This is the stuff I mentioned, the sequential reading and 1 thread, 4 threads, and these are the results. So we chose a mid-range size of 1 kilobyte. With 1 kilobyte size, you still have effects of overhead per entry, but it's not very problematically large. So if you get below kilobyte, you'll already experience quite strong degradation from the overhead. So I tested with 100 million entries. That's 100 gigabytes of data in one node with parallelism of 4. And these are the throughput was 365,000 ops per second. And the store was able to reload in 82 seconds. So the net speed of reloading was 1.2 gigabytes per second. And the raw reading throughput, because you have garbage on disk, so you have to read all the garbage. You cannot decide in advance what to read and what not to read. So the raw reading throughput was 1.4 gigabytes per second, where like the theoretical maximum of just raw reading, doing nothing else, no housekeeping at all, would be 1.8 gigabytes per second. And I had it measured on Amazon. On Amazon, it's completely different. It's not such high-end SSD that you get. In this case, parallelism is no longer so beneficial because the disk is just slow. So it doesn't matter if you add more parallelism. So I tested with parallelism of 2 and arrived at these numbers. So they are less, but they are still quite good compared to what the raw hardware can do for you. We got raw readings throughput 360 megabytes per second, and I think it's like 450 megabytes per second is what you can get with just reading and nothing else. I can end here. We can go to questions. This is about future use cases planned. So this is about larger perspective of hot restart as a feature used in Hazelcast, but we can go to questions now, I think.
We have time for one question. Basically, you're intercepting memory write and storing into hard disk, aren't you? So isn't your Hazelcast performance limited by your input-output system on computer now?
You mean in memory?
Yeah, you're in memory. If they're completely synchronized, now you have limit on how fast Hazelcast works.
Yes, you cannot beat the throughput of the
so
SSD.
You don't have any lag or buffer between memory state and...
There is a buffer and everything, but in the end it's throughput. If you have system operating for a longer time at maximum possible load, you'll end up with hard disk or SSD being your bottleneck. There is no way around it. Either you want persistence or you don't. But we are here to make it as fast as close to the raw speed of the SSD as possible. That's the job of this system.
Okay, thanks.